Let's start with an easy one. Number 7, we're told that we've got a string vibrating as shown in the picture. That's obviously a standing wave, and I count 1, 2, 3, 4 antinodes, which tells us that this is the fourth harmonic, and we're also given the frequency. So at 100 hertz, the string sets up a standing wave, which must be the fourth harmonic. And then they're asking us, if the frequency is turned up to 200 hertz, how many antinodes will we have? Well, you could just blindly guess. Twice the frequency could mean twice the number of antinodes, so from 4 to 8. But let's show this with formulas. We know that in general, the frequency of the mth, is that a word? Mth mode is m times the frequency of the fundamental. And since I count 4 antinodes, this has to be the fourth harmonic. So we know immediately that the frequency of the fourth harmonic is 4 times the fundamental frequency. Since we know this frequency, it's given to us as 100 hertz, we can solve immediately for the fundamental frequency. It's got to be F4 over 4, which is 100 hertz over 4. Okay, so the fundamental frequency is 25 hertz. That was easy. Now, if you had started out with writing that the frequency of the mth harmonic is, you could write the more complete formula, m times v over 2L. And we know that the speed is the square root of the tension over the mass density. If you had started with this, and that's not a bad way to start, just writing down the formulas that you know are relevant, figuring out what to do with those formulas, you may have gotten a little confused at that point because you're thinking, well, they didn't give us the tension and they didn't give us the mass density. They also didn't give us the length of the string. How am I supposed to find these quantities? You don't actually need to. Now that we know the fundamental is 25, we can say that the, let's see here, what am I doing? Oh, right. So F sub M is equal to M times F naught. Well, in part A, the number of antinodes is what's unknown. And what's given is the frequency. So we know that we're now talking about a frequency of 200. I've just determined the fundamental frequency, that's the frequency of the first harmonic. So that allows us to find M. 200 hertz is M times 25 hertz. M must be 8. So my initial guess is correct. This will change to a mode with 8 antinodes. Is there another way to do this even? You could also recognize that in this formula, F sub M equals number of antinodes times fundamental frequency. What's the thing that's not changing here? Since there's no mention of tightening the string, so the tension's not changing. And we're not changing the string itself, so the mass density is not changing. We're also not changing the length of the string. In other words, the fundamental frequency, F naught, is not changing. I really should not have called that F naught. I like to use that subscript 0 for like initial value, but it's really F1, right? This is bad notation. If I were to redo this problem, I would go with F1, because when you plug in the integer 1, you get F sub 1 equals F naught. So the fundamental frequency should really be called F1. Let me change that. F1. Okay, this doesn't change. So that technique where you put all the stuff that could change on one side and the stuff that doesn't change on the other side, that would look like this. Fm over m equals F1. This is a constant. It's also true that the new frequency, 200 hertz, I'll call that Fm prime over the new number of antinodes, m prime, has to equal F1. So this ratio doesn't change. As you change the frequency of the string, it's going to pop into a different standing wave. with a different number of antinodes, but the ratio doesn't change because the ratio is equal to this unchanging fundamental frequency. So I could say, I could set these two equal to each other and say Fm over m equals Fm prime over m prime. This is the frequency, the new frequency, 200 hertz. This is the number of antinodes in that, or at that frequency. This is the original 100 hertz, and this is the 4 antinodes. So solve this for the new number of antinodes, and you get m prime is equal to Fm prime over Fm times m. In other words, the new number of antinodes is the new frequency 200 hertz compared to the old frequency 100 hertz times 4. And this in symbols is exactly what I said at the beginning, that perhaps the number of antinodes is proportional to the frequency. So since we've doubled the frequency, we should have doubled the number of antinodes. This almost seems more complicated, doesn't it? For this particular problem, it wasn't necessary to do this, but this is a very efficient technique in a lot of problems. We're not done with this problem yet. In part B, they're saying, okay, now we increase the tension in the string to 4 times its original value, and we would like the picture to look the same. Now, generally, when you increase the frequency of a wave on the same string, since you haven't changed the speed, the wavelength would get, now, the wavelength would get shorter, but we don't want the wavelength to get shorter. We want it to stay the same. Although it's not really the frequency that's the cause here. We're thinking about this causally as tension. So we know that if you increase the tension, you increase the speed of the wave. And increasing the speed tends to also increase the wavelength, right? Because the pulses travel farther. So in order to compensate for that greater speed, if we want the wavelength to stay the same, we're going to have to jiggle the string faster. So causally, that's how you could think about it. Now, why don't we relate the new speed to the old speed? So V prime, I'll call the new speed V prime. It's the square root of T prime over mu, which is the square root of 4 times the old tension over mu. We can bring out the square root of 4, which is 2. And we recognize this is the old speed before the tension was increased. So this is 2 times the original speed. Now, the fundamental frequency is V over 2L. Wave speed, length of the string. So that means that the new fundamental frequency, since we've increased the tension, that's going to change all the harmonics. F1 prime for me right now is the new fundamental frequency with the new tension. So that's going to be V prime over 2L. We've just determined that's 2 V over 2L. Well, that would be 2 times the original fundamental frequency, right? Because V over 2L is the original fundamental frequency. So now all we have to do is go back to the formula for the frequency of the mth harmonic. So with this new tension, Fm prime, the frequency of the mth harmonic in the new, primed system, if you want to call it that, is m times F1 prime. Now that we've determined the fundamental frequency, and let me finish that calculation. Previously, the fundamental frequency was 25 hertz, right? So now it's 50 hertz. At this higher tension, 4 times the tension, which means twice the wave speed, the fundamental harmonic is 50 hertz, or fundamental frequency. And so if we want the string to look the same, we're still counting 4 antinodes. So now that frequency's got to be 4 times 50 hertz. In other words, 200 hertz. So 200 hertz will now produce the 4th mode. Is there another way to look at that? Well, since the picture isn't changing, that means the wavelength is not changing. You can see that the wavelength, this is one wavelength, that's still half the length of the string. That's not going to change. So if we go back to the fundamental relation for waves, which says that frequency times wavelength equals speed, you can solve this for the quantity that doesn't change. And I guess I could write it this way. Speed divided by frequency is lambda. That's a constant. So we could say new speed over new frequency equals old speed over old frequency. The ratios must be the same because they're both equal to the unchanging wavelength. We'd like the picture to look the same before and after we increase the tension. And what we're solving for is the new frequency. So I get, after moving some stuff around, that the new frequency is simply the ratio of the speeds on the string to the old frequency. Well, the old frequency was that 100 hertz. And so I'm not talking about fundamental frequencies. I'm talking about the actual frequency at which the string was vibrating. They told us originally it was 100 hertz. That's F right here. And we've already determined, using the proportional reasoning here, that the ratio of the speeds is 2. The new speed is double the old speed. So this is just going to be 2 times 100 hertz. That's another way to go about it. This next one is simple but interesting. We're supposed to model the air within the human vocal apparatus, I guess you could say, as an open, closed tube. So when you produce sounds, when you sing or speak, you've got vibrating air all the way from your lips down to your diaphragm. And I don't really understand that because it looks like this junk connects to your lungs. How does the air get all the way down to your diaphragm? I don't know. Anatomy is probably complicated. Now, your lungs are not simply open vessels. They're not just like tanks. There's a bunch of stuff in there. So this is, I'm sure, an approximation, but that's what the book is telling us to do. So we'll go with that. We're supposed to figure out what the distance is from your open mouth to your diaphragm. And if I had to guess, I would say it's less than a meter and it's more than 10 centimeters. So it's somewhere between 10 and 100 centimeters. Now they said open, closed tube. Clearly, when you're speaking, your mouth is open. So that would be a pressure node. The pressure's got to match the pressure of the atmosphere, or a displacement antinode. And I guess because the diaphragm is, the air is sealed off. It's not like the air can leak out into the rest of your body. I hope not. So that would have to be a displacement node or pressure antinode. So this is definitely an open, closed tube. If you're going to model it as any of those 3 cases, open, open, closed, closed, or open, closed, it would have to be open, closed. So we're supposed to calculate the approximate length knowing the fundamental frequency. So we're told that the fundamental frequency is in the ballpark of 250 hertz. Now let me elaborate on that a bit. If you just sing a tone that's comfortable in the range of your voice, that's really not one frequency. If when you sang the most comfortable tone you can within your range, and it only produced one pitch, then you would sound exactly like everybody else. There would be nothing to distinguish the quality of your voice from somebody else's. What's actually happening when you sing that one tone is you've got a whole bunch of harmonics which are being excited simultaneously, and they all have different strengths, so to speak. And the ratio of those amplitudes is what makes your voice unique, like literally your voice unique. So we're just talking about the fundamental. And the range of human hearing, at least for a young person, goes from like 20 hertz all the way up to 20,000 hertz. This is less than 1 kilohertz. So this is definitely in the lower part of the range of the human voice. Okay, well, For an open closed tube, the set of harmonics have frequencies given by, well, I've written down here the formula for the fundamental frequency. If you don't remember where that came from, remember for an open closed tube, the length of the tube has to be an odd multiple of quarter wavelengths. This is the different situation from open, open, close, close. So if you combine that with the fact that frequency is speed over wavelength, you can take this formula, solve it for lambda. Let's do that right now. For the fundamental, you go with m equals 1. So lambda would have to be 4 times the length of the tube. You plug that in here, and that's where this comes from. Now, they tell us that the speed of the air inside your larynx or whatever is something like 350 meters per second. Now, that's faster than the normal 343 that we use for room temperature because the air is going to be warmer inside your body. So we just have to plug that number in, plug in the known frequency, and this would be easy to measure with an oscilloscope and a microphone, and we solve for L. 4 times, oops, I'm not doing that right. L would have to be the speed of the wave divided by 4 times the fundamental. So 350, whoops. Hey, just yell at me when I do that, okay? Sometimes I don't realize I've got my writing off the page. 350 meters per second over 4 times the fundamental of 250. Hey, that's easy. They must have picked these numbers on purpose. 4 times 250 is 1,000. So we just take the decimal place 3 to the left. This is not meters per second. It's just per second, right? Hertz is inverse second. So 0.35 meters, which is 35 centimeters. So it wasn't a very precise guess, but my guess was correct that the voice, the column of air involved in your voice apparatus is between 10 and 100 centimeters. Number 20 from chapter 17 requires a wee bit of knowledge about the violin. If one of these strings is plucked or bowed and it's not being pushed down at any point along the neck, then it will vibrate in several harmonics simultaneously, but the one that we perceive as being dominant is the fundamental. So let's take this bottom string here. This would be a node. That is called the bridge. I just looked that up. And then the other node would be over here at what is called evidently the nut. So there are no other nodes between those two if you're talking about the fundamental. Now you can make the same string sound a higher pitch or produce a tone at a higher pitch by changing its effective length. So here the player is pushing down on the string, so it's only free to vibrate between where her finger is and where the bridge is. So she's effectively shortened the string. The part of the string on the other side of her finger is not going to vibrate because it's not being bowed or plucked. Okay, so we're supposed to figure out how to produce a pitch of a given or desired frequency by figuring out where to place the finger. And what's a little confusing about the wording of the problem is they ask, how far from the end of the string should she press down on the string? Well, which end? Because if you're talking about the bridge as the end, then you would specify this distance, which is really the effective vibrating length of the string. If they mean the nut as the end, then that would be this distance. And so we would have to take the total distance between the nut and the bridge and subtract the effective vibrating length of the string. Turns out they do mean by the end of the string, they mean the nut. So at the end, we'll subtract the vibrating length of the string from the total length. And the total length would be the length it would be the length of the string in the fundamental mode when you're not pressing down on it. So keep in mind, the string is actually wrapped around these screws a bunch of times. So the real length of the string is even longer. The two lengths we're talking about are the effective vibrating lengths of the string in the two modes. Okay, so here's the nut, here's the bridge. Let's do this. we're told that when you're not pressing down on the string, the A string vibrates in its fundamental at 440 hertz. That's the first harmonic of the A string. Now, I'm not talking about a C string. You can make the A string vibrate and produce a tone called C, the note C, which has this this frequency. So we're not forcing the A string to vibrate in a different harmonic, right? It's not like we're going to get this to vibrate with two antinodes. What we're actually doing is changing the length of the string. That's different than just putting the string into a different mode of vibration. In both cases, it's the fundamental mode. So here's the A string vibrating in its first harmonic, also known as fundamental. And then here's the A string, which has been shortened by pressing down with your finger, vibrating in its new fundamental mode. Okay, well, we know that the fundamental mode is 1 times V over 2L. V is not changing, right? You can't change the speed of the wave on the string just by pressing down on the string. To change the speed, you would have to change the tension in the string by turning the screws, the tuning screws, or by changing the mass density of the string. We're not doing either of those things, so it's really just L that we're changing. So the quickest way to solve this would probably be to recognize that the ratio of FC to FA, remember, these are both fundamental frequencies. Well, that would be V over 2 times the length associated with the note C divided by V over 2 times the length associated with this, the note A. So this is L sub C and L sub A. Formula for fundamental frequency divided by formula for fundamental frequency. And you see that we don't actually need to know the speed of the waves. They cancel. So does that factor of 2. So FC over FA is equal to the reciprocal ratio of the lengths. See how we've got a denominator and a denominator? So that flips them. This L sub A comes up top. Okay, and we solve this for, what are we solving for? We're given the frequencies. We're actually given L sub A. We know that the total length of the string, the A string between the bridge and the nut, is 30 centimeters. So we know this quantity. We're trying to find L sub C. Looks to me that L sub C would be FA over FC times L sub A. So this ratio is going to be, did I do this wrong? LC, no, I don't think so. Right, FA 440 divided by 523. This is a number less than 1. So the string is made shorter as expected. 440 divided by 523, and we multiply that by the 30 centimeters. Just how, oh, I did it again. Just how long does the string need to be? Divided by 523 times 30. 25.2 centimeters. That's this length. Yeah. But what they're really asking is how far down from the nut should you press down the string? Evidently, that would be 4.8 centimeters. And that's exactly how violinists play, right? Itzhak Perlman, for instance, every time he wants to play a note, and sometimes you're playing 5 or 10 notes per second, you do a mental calculation. You use this formula to figure out how far you need to press your finger from the nut. Of course, that's not how they do it. It's muscle memory, talent. Talent and practice, lots and lots of practice. Just like physics, right? The more you practice these problems, the better you get at them. Let's solve number 22 using some simple reasoning. First, we'll do that first, and then later we'll try to use some formulas and be a little more formal about it. We've got 2 speakers sending sound in the same direction. Somebody standing over here notices that the sound is at a maximum, excuse me. The intensity of the sound is at a maximum when the speakers are 20 centimeters apart. So I've drawn the waves in phase, max constructive interference. Then one of the speakers is scooted so that the distance between them is now 60 centimeters. And that's the first point during the scoot at which the sound falls to a minimum of intensity. So that would be max destructive interference. Well, from 20 to 60, obviously, is another 40 centimeters. And if we just use common sense, if you were to scoot them by a full wavelength, they'd be right back where they started in terms of their phase difference. So scooting by half a wavelength would switch from maximum to minimum destructive interference, or from minimum to maximum. Does that make sense? Scooting by half a wavelength will just switch from one to the other. And that's what's happened. We've gone from max to max constructive. Did I say max or min? I should have said max constructive interference to max destructive interference. That means a scoot of half a wavelength. So evidently 40 centimeters is half a wavelength, and that tells us that the wavelength is 80 centimeters. That's what they're asking for in part A. What's the wavelength? Let's see if we can be a little more formal about it. I'm going to use this formula that says the total phase difference between the two sources is the phase difference due to their path length difference, right? First, you compare the path length difference to the wavelength, take that fraction times 2 pi, and then plus any inherent phase difference. Sorry, this is kind of cramped. Let me write it bigger here. So in situation 1, the total phase difference is the path length difference in situation 1 compared to the wavelength times 2 pi, and then plus delta phi sub 0. And evidently that path, or that total phase difference, has to be 0 or 2 pi or 4 pi. It doesn't really matter which of those numbers you pick, but we know that for max constructive interference, the total phase difference has to be some multiple of 2 pi. I could go with 0. How about I just go with 2 pi? Again, the outcome, the answer that we get will not depend on your choice of 0 or 2 pi or 4 pi, etc. Now the phase difference in situation 2, well, that's the new path length difference, delta x sub 2, times the, and you know what I should have labeled? Oh, right. This is the inherent phase difference, right? That has to do with how they're being driven in time. And I don't need to specify situation 1 or situation 2 because that's not being changed. All that's changing is the relative position of the speakers. And I'm going to set that equal to pi. I could do 3 pi. I could do 5 pi. All right, let's go with 3 pi. I guess that makes a little more sense since we're increasing the separation. But again, the answer will not depend on your choice of 3 pi or 1 pi or 5 pi. All that really matters is that we go with an even multiple of pi and an odd multiple of pi. Okay. Now, what have I done here? Let's subtract both equations. This is a quick algebraic technique. We'll go equation 2 minus equation 1. Well, when we take this and subtract that, the phis go away. And here I'm going to factor out the 2 pi over lambda. And I've got delta x for situation 2 minus delta x for situation 1. And 3 pi minus 2 pi is pi. And I find, well, we can divide the pi from both sides, divide the 2. I find that delta x sub 2 minus delta x sub 1 has to be lambda over 2. So that means lambda over 2, I guess I've switched the sides here. Well, this would be the 60 centimeters minus the original path length difference of 20 centimeters. That's 40 centimeters. And it's just the same statement I made to begin with, that evidently half a wavelength is 40 centimeters. If scooting the speaker makes you go from max constructive to max destructive, you just pushed your speaker by 1 half a wavelength. That's easy to see in the picture here, right? This distance is one full wavelength, peak to peak. So imagine scooting this speaker so that this peak ends up over here. Won't the two speakers still be in phase? Sliding by one wavelength to the left or one wavelength to the right doesn't change the condition of constructive interference, max constructive. Same thing for 2 wavelengths, 3 wavelengths. Okay, what are they asking for in part B? This is the one where they'd like to know if you continue to scoot this speaker, the bottom speaker, to the right, how long will you have to, or how far will you have to scoot it before you're back to max constructive interference? You could just look at it graphically. We've already determined that this distance is 80 centimeters. That's the wavelength. And that means half a wavelength is 40 centimeters. So to bring this peak into alignment with this peak, we're going to have to slide it by an additional 40 centimeters, which will bring us to a total separation of 100 centimeters. Or just recognize that since scooting by half a wavelength makes you go from max constructive to max destructive and vice versa, we're already at max destructive interference when they're separated by 60 centimeters. Just push ahead another half wavelength to get back to max constructive. That would be another 40 centimeters. If you're going to go with just the simpler reasoning, if you saw a problem like this on an exam, you would need to provide some kind of justification. So write a couple sentences, use symbols if you can. It's not always necessary to do this exactly, but you have to provide some kind of justification. Number 26 is a problem involving thin film interference. We've got a thin layer of oil, that's the film, resting on top of water. The indices of refraction are given. And this is a case where each index of refraction is greater than the last. 1, 1.25, 1.33. So we can draw incoming light rays of a particular frequency. Now, we know that anytime light reflects off a boundary where the transmitted light would be in a medium with higher index of refraction, you get that inversion. So we can represent that with one of these transverse oscillations, and then I'll have it being reflected inverted. Not the best picture, but hopefully you see the inversion there. And then really the second wave splits off from the first one, but I have to show them in different places on the page so you can see that. Okay. This one also experiences an inversion, in other words, a phase shift of pi. And this outgoing wave and this outgoing wave, or reflected waves, they're going to interfere. And we're supposed to figure out what's the thinnest film that will produce constructive interference for this wavelength of light, which is green, by the way. And that's the wavelength in vacuum. Okay, well, I'm going to try to use simple reasoning first, and then we'll be a little more precise with the formula. Well, the beam of light that produced both of these reflections obviously was in phase with itself. That's what we're imagining, that all the waves within that beam were in phase. In other words, an inherent phase difference of 0. But then each reflected wave picks up a phase shift of pi. Since they both experience the same phase shift of pi, then they're still in phase in time. They still have an inherent phase difference of 0 in time. I'm talking about like the leading edge of the waves. So that means we really only have to worry about the additional contribution from the path length difference. Now, we just talked about this in the previous problem. You still have constructive interference if the path length difference is 1 wavelength or 2 wavelengths, etc. So let's set the total path length difference equal to an integer number of full wavelengths. That's wavelengths in the oil, though, because the extra path length is inside the oil. This wave has to travel d down and d up in the oil. So we have to use the wavelength in the oil. And to get that, we just take the vacuum wavelength, remember, and divide by the index of refraction in the oil. Now they're asking for, yeah, so this is the wavelength in vacuum. They're asking for the smallest layer or the smallest thickness of oil that will do it. So let's solve for the possible values of that thickness D. I get m times lambda over 2n oil. Okay, well, the smallest one obviously is the one where we let m equal 1. You can't plug in m equals 0 because that's a layer of no thickness. That's not going to work. So that goes to just lambda over 2n oil. Let's figure out what that's going to be. We take, I'll leave my answer in nanometers. So 500 nanometers divided by 2 divided by the oil's refractive index. And I get 200 nanometers, which is pretty darn skinny. That's 0.2 micrometers if you're interested. And for comparison, your hair, one strand of your hair is something like 50 micrometers thick. So this is, well, 50 times 5. So it's way smaller than the thickness of your hair. Okay, is there a part B to this problem? No, but can we be a little more formal about this? Well, we could look at the total phase difference between the reflected waves and use our trusty formula. It's got the contribution from the path length difference plus the inherent phase difference. And the condition for constructive interference, excuse me, is that, I'm looking for some scrap paper, is that the total phase difference be equal to, was I off screen again? My bad. That the total phase difference be equal to a multiple of 2 pi, right? As long as it's an even multiple of pi, in other words, a multiple of 2 pi. So that's got to be some integer times 2 pi. Now, here's something I really should have emphasized more in the lecture videos. If the inherent phase difference is 0, this equation reduces to something even simpler and easier to think about. So the way I'm approaching this problem is I'm regarding this quantity as being 0. Since both reflections involve a phase shift of pi, they're both still in phase inherently or in time. There's no difference in phase in time with their oscillations. So I'm capturing that information by setting the inherent phase difference equal to 0. Okay, so for 0 inherent phase difference, the only contribution comes from the path length difference. And look at this, the 2 pi's cancel, and we find that the path length difference needs to be an integer number of wavelengths. Really simple result. If the inherent phase difference is 0, then the condition on the path length difference, if you desire constructive interference, is simply that the path length difference be lambda or 2 lambda or 3 lambda, etc. Okay. So if I do that, I'm going to wind up at the same formula. That's really what I'm saying here, right? The total path length difference is 2 times d, thickness down, thickness up, and I'm setting that equal to an integer number of wavelengths in the medium. Next up is a simple graphical problem. Maybe a little silly for me to go through this, but we'll do it for thoroughness. The numbers 1 and 2 indicate 2 sources of spherical wavefronts or circular wavefronts. Part A is asking us, are they in phase or not? And when they say in phase, that's short for, is their inherent phase difference equal to 0 or pi or 2 pi or 3 pi, etc. Well, this is a snapshot graph. Time is frozen. And since these sources are in the same medium, the ripples coming out of source 2 travel at the same speed as the ripples coming out of source 1. So look at the distance between this innermost ripple and source 2. That distance is the same as the distance, or the radius, I should say, of the innermost ripple around source 1. So the if the distance, if those two distances or those two radii are the same and the speed is the same, then the time it took for the ripples to get here from each source is also the same. In other words, if you just roll back the clock, these innermost ripples were emitted at the same time, sometime in the past. In fact, it would have been one period before this picture is taken. You can see that sources 1 and 2 would just now be emitting another wavefront. So these two sources are definitely in phase. In other words, they have an inherent phase difference of 0. They would be out of phase if this, like let's say, for instance, source 2 had this ring farther out already and it was emitting, if you had drawn a ring halfway between source 2 and this ring, but you kept source 1's picture the same, that would indicate that they were emitting their crests at different times, maybe half a period apart. They would be out of phase. Okay, then we're supposed to make a table and figure out whether the interference at these 3 points, P, Q, and R, is destructive or constructive. And we just assume in each case it's maximum constructive or destructive. Okay, so let's just go through this one at a time. Point P, well, you can see that a circle from Q and a circle from, I'm sorry, not Q, a circle from source 2 and a circle from source 1 intersect at point P. Those two wavefronts are arriving at the same time. And when I say wavefront, I'm really talking about like the peaks from the sources. That means constructive interference, max constructive interference. Half a period later, like if you could run this animation and wait 1/2 a period, you would then see that there was not a circle here from either source 1 or source 2. You would actually be looking at a point halfway between. Point P would be a point halfway between two circles from 2 and two circles from 1. So the two valleys from the sources would be lining up. That's still max constructive interference. So rather than completing this problem with that sort of reasoning, let's use path length difference. We've already concluded that the inherent phase difference is 0, and that means the only thing we have to worry about is the path length difference. If the path length difference is lambda, 2 lambda, 3 lambda, etc., that's max constructive. If it's half a wavelength, 3/2 wavelengths, 5/2 wavelengths, in other words, an odd number of half wavelengths, that's max destructive. Okay, how far is P from source 1? I count 1, 2, 3 wavelengths. How far is it from 2? 1, 2, 3, 4 wavelengths. So P is 3 wavelengths from source 1, 4 wavelengths from source 2. So the path length difference would be the distance between, or the difference between these two. I'm just going to go with absolute value. So that's 1 wavelength difference. Whichever one has to travel farther, that would be source 2. During that 1 extra wavelength that it took that it had to travel. No, let me rephrase that. How long did it take source 2's wave to travel that extra wavelength? It took 1 period. What was source 1 doing during that 1 period? It was oscillating 1 more time. So the 2 waves still arrive in phase. That's max constructive. Point Q. Okay, I count that I'm going to start with source 1. 1, 2, 3, 3.5 wavelengths from source 1, and only 1, 2 wavelengths from source 2. 3.5 and 2. 3.5 wavelengths from source 1 and 2 wavelengths from source 2. The difference between those is 1.5 wavelengths. Well, anytime you get a half integer number of wavelengths, in other words, 1/2, 3/2, 5/2, that's max destructive. So 2 different ways of saying that in words: half integer number of wavelengths, or you could say an odd multiple of half wavelengths. Am I doing that right? 1/2, 3/2, 5/2. Yeah, those are all half integers. Takes me a while to switch screens here. Okay, now the other way to arrive at the same conclusion, destructive interference at point Q, is to recognize that Q is on, it's on a peak from source 2, but it's in between this peak and this peak for source 1. In other words, it's at a valley at the present moment from source 1. So the valleys of source 1 are overlapping with the peaks of source 2 here at point Q. And half a period later, it'll be switched. It'll be a peak from source 1 and a valley from source 2. Okay, last one, R. Let's do this one quickly. R is 1, 2, 2.5 wavelengths from source 1, and it's 1, 2, 3.5 wavelengths from source 2. Did I say that right? Oh, I've already forgotten it. Is it 2.5 and 3.5? I'm going to trust my memory. Okay. So it doesn't matter that we've got a half integer number of wavelengths being the path length for each source individually. All that matters is the path length difference, which in this case is actually a whole wavelength. So that is constructive interference. Despite the fact that we've got half integers for R1 and R2, what matters is the path length difference. Can we interpret that one more way? Let's look at point R. Would you agree that since this is a peak from source 1 and this is a peak from source 1, R is sitting at a valley from source 1. It's also sitting at a valley from source 2. Here's a peak from source 2, a peak from source 2. So of the valleys from source 1 and 2 are being superposed. That's still max constructive interference. This one's a little more interesting because we're in 2 dimensions and we'll have to look at the geometry of a triangle. We've got 2 radio antennas or transmitting antennas. They're both transmitting at the same frequency, 3 megahertz. That capital M is for million. And that's typical for radio waves, that frequency. In fact, if you like to listen to KFI 640, that's 640 kilohertz. KNX 1070, that's around, well, 1070 is around the number 1000. That's really 1000 kilohertz. The AM dial expresses all of its frequencies in kilohertz. So 1000 kilohertz, well, that would be a million hertz, 1 megahertz. Okay, so the AM dial is like half a megahertz, 1 megahertz. Here we're talking about 3 megahertz radio waves. And if you're curious, radio stations like 99.1, that's also megahertz. So the FM dial is around 100 megahertz. AM dial is around 1 megahertz. Here we've got 3 megahertz. Okay. And we're told that these antennas are out of phase, which means that their inherent phase difference is pi. So they're oscillating out of phase in time. And I sort of tried to represent that by showing that there's a wave crest that's just leaving this antenna, but it's already left this one. So we know that the inherent phase difference in the 2 sources is pi. And they would like to know, is this point right here a point of constructive or destructive interference? Now, we've already looked at the interference pattern from 2 sources, even 2 out of phase sources, using the Falstad ripple tank. So we know that there are hyperbole, which we call nodal lines and antinodal lines. They're not really lines, they're curves. So this could be on either, or it could be somewhere in the middle. We need to know the path length difference. So how about I call this source 1 and this source 2? R1 is the distance from source 1 to the place where we're evaluating the type of interference. And R2 would be the hypotenuse of this triangle. Oh no, we have to use Pythagorean theorem. There's a square root in this problem. Ugh. Okay, well, the coordinates of this point we're told are 300 meters and 800 meters. Not to scale, you'll have to pardon me. Okay, well, R1 is clearly 800 meters. It's just the y coordinate, the absolute value of the y coordinate. To get R2, we'll have to use Pythagorean theorem. So I'm really going to use the distance formula. For those of you who haven't seen that in a while, if you have the coordinates x1, y1 of one point and x2, y2 of another point, the distance between those 2 points is the square root of the difference in their x coordinates squared plus the difference in their y coordinates squared. That's just Pythagorean theorem, right? This side length would be this x coordinate minus this x coordinate, and this side length would be this y coordinate minus this y coordinate. Take those two side lengths, square them, add them up, take the square root. That's Pythagorean theorem. So R2 would be the square root of, well, this has an x coordinate of 300. 300 minus negative 300. And I'd have to square, what did I just say? I'd have to square that. That's my delta x squared. And of course, you could have just recognized that the length of this side is 600. 300 plus 300. Plus the 800 squared. Okay. 600 squared plus 800 squared. Ooh, I can do this one in my head because I know that 3, 4, 5 is a Pythagorean triplet. 3 squared plus 4 squared is 5 squared, right? 9 plus 16 is 25. And any multiple of a Pythagorean triplet is also a Pythagorean triplet. So if I multiply this set by 2, I get 6, 8, 10. So I know that 6 squared plus 8 squared is 10 squared, right? 36 plus 64 is 100. And if I just multiply this now by 100, am I doing this right? Yeah, then I've got these numbers. Then I'd have 600, 800, and 1,000. So the distance must be 1,000. But because I'm compulsive and don't trust myself, even to add 2 plus 2, I will do it in the calculator. Are you like me? 600 squared plus 800 squared equals, take the square root, and of course it's 1,000. So delta R is 1,000 minus 800, 200 meters. This wave has to travel 200 meters farther to get to the what I'll call the field point than this wave does. Now, how does that compare to a wavelength? Because we need to know that in order to calculate the overall phase difference. Well, it's easy to calculate the wavelength using the fundamental relation for waves. We take the wave speed and we divide by the frequency. And in this case, the speed is really the speed of light, which is 3 times 10 to the 8th meters per second. And the frequency has that nice number, or is that nice number, 3 times 10 to the 6th hertz. So you can see the 3's cancel. 10 to the 8th divided by 10 to the 6th. We just subtract the powers, and that's 100 meters. So it's pretty common, actually, to describe frequencies of light using wavelength. When you're talking about radio waves, astronomers do this, electrical engineers do this. They'll talk about 2 centimeter waves or millimeter waves rather than giving the actual frequency in hertz. Okay. Well, the path length difference is double the wavelength. Now, if the only phase difference were due to path length difference, then an integer number of wavelengths would actually mean constructive interference. But we've already got this phase shift of pi inherently. So if you're already out of phase by pi, and then you have a path length difference of lambda or 2 lambda or 3 lambda, you're still out of phase. So the answer is destructive interference. Now, if we want to use the formula, we could say that the total phase difference would be the contribution from, and this time I have to use delta R because we're in 2 dimensions, the contribution from path length difference plus the inherent phase difference. So that's going to be 200 meters compared to 100 meters times 2 pi plus delta phi sub 0. Well, that's 2 times 2 pi, so 4 pi. And I should have actually substituted here. Plus pi. It's an odd multiple of pi. That means destructive interference. Now, it doesn't really matter if this comes out to be 4 pi or 6 pi or 8 pi. If you think about it, it all boils down to this property. If you add two even numbers, you get another even number. If you add two odd numbers, you get an even number. Maybe I should just write this down. Even plus even is another even number. An odd number plus an odd number is an even number. And an odd number plus an even number is an odd number. And odd numbers, an odd number overall corresponds to destructive interference, and an even number overall corresponds to constructive. Huh. All of these problems can really be solved that way. When I'm saying odd number, I'm talking about an odd multiple of pi. So you're adding a phase shift contribution from the path length difference and also one from the inherent phase difference. If you think of each of those contributions as some multiple of pi, all you have to worry about is whether it's an even multiple or an odd multiple. And even though this works, and it's probably the best, most efficient, or quickest way to think about these problems, it won't be enough just to do this on an exam. You have to show me a little more than that. Well, not just a little more, but show what you can. But this is a good way to think about it. Those last problems were called exercises by your book. And those are supposed to be a little easier, a little more straightforward. Now we're looking at a problem, a proper problem, because it's under the problem category at the end of the chapter. We're told that a string is vibrating in its third harmonic, which is why I've drawn 3 antinodes. And 30 centimeters in from one end, we're told that the string is vibrating at half of the maximum amplitude. Each of these particles, if you'll recall, is oscillating up and down in simple harmonic motion. This particle has an amplitude that's less than this particle. The particle here at the antinode experiences the greatest amplitude of oscillation. The particle at the node has 0 amplitude of oscillation. So all we know is 30 centimeters in, that particle is jiggling up and down with 1/2 the amplitude of the max amplitude, meaning the amplitude at the antinode. So here I've blown up this leftmost half wavelength, and we'll indicate, let's see here, since this is the total amplitude or the max amplitude, it looks to me like right about here would be half of the maximum amplitude. So this is I'm sorry, 1/2 of max amplitude, half max amplitude. This is the max amplitude. And so we need to know that this is 30 centimeters from one end. We will be using that fact. What are we looking for here? I forgot to say that. How long is the string? What's the total length of the string? That is the variable that we seek. Let's do this a couple ways. First, we'll follow the lead of the solutions manual. I'm going to remind you that the displacement function for a standing wave looks something like this. It's 2 times the amplitude of each individual wave, and then you've got sine of kx cosine of omega t. This is the part that makes all the particles jiggle up and down. This is what your book called the amplitude function. Well, in this problem, 2a is that max amplitude. 2 times lowercase a is the same as this. So let's just write over that and call that a max. Amax. Isn't that a realtor? That sounds familiar, like an insurance company. Okay. Well, the amplitude has nothing to do with this. This is just the part that makes everything go up and down. This is what determines the amplitude. At different values of x, you plug in different coordinates, the sine function takes on different values, that gives you a different amplitude. So at amplitude equal to 1/2 max amplitude, well, the only way for that to happen is if the sine function takes on the value 1/2 sine of kx needs to be 1/2. Simple as that, right? Then you've got a factor of 1/2 next to the a sub max. Well, we know what the x coordinate is. We're told that that happens. Why don't we just put the origin here at the left end of the string? So then the coordinate of the point at which the amplitude function takes on a value of 1/2 a max, that coordinate is 30 centimeters. Well, but we also need to know what k is. So let's do this. K, we know, is 2 pi over the wavelength. We can also relate the wavelength to the length. We're being asked to find the length of the string. So obviously the number L has to appear somewhere in these calculations. Oh, I got to sneeze. Okay, I used the pause button and spared you from the onslaught. Do you remember this requirement? Lambda has to be 2L over the number of antinodes. You can also just recognize that the length of the string has to be an integer number of half wavelengths. That's the same condition. Well, the number of antinodes we're talking about is 3. So this is 2 pi over, plug in 3 for the number of antinodes, 2/3 L. So we know what k is now. We know what the wave number is. You'll notice that the 2's cancel, and we can write this as 3 pi over L. Okay, so we go back over here and we say that the sine of 3 pi over L times 30 centimeters, which is 0.30 meters, has to equal, I guess I can put the m for meters, has to equal 1/2. Okay, now we just need to get the argument by itself. That means we need to undo the sine function, and then we'll solve for L. Also, there's an assumption here I didn't point out, and the solutions manual makes the same assumption. It could have been that the 30 centimeters was actually here or here. See, these are other positions where the amplitude is 1/2 of the max amplitude. So we're just assuming that the 30 centimeters is the first point at which you encounter half the amplitude. We're supposed to make that assumption. If it was somewhere else, then you're going to end up, I believe, with a different number for the length of the string. Yeah, obviously, if this is 30 centimeters, that's going to give a much longer length for the string than if this was 30 centimeters or this was 30 centimeters. How do we undo the sine function? We take the inverse sine. You could also do this. What angle has a sine of 1/2? What's the angle that has a sine of 1/2? I just repeated myself. I was trying to say it a different way and couldn't come up with anything. Well, I know that the sine of 30 degrees is 1/2. So all of this junk inside the sine function is 30 degrees. Of course, we have to express that in radians, which would be pi over, well, I'm drawing a blank here. 30 degrees is 1/3 of 90, so that's pi over 6. This is what happens when you're a little low on sleep. Pi over 6, is that 30 degrees? Yeah, because 60 degrees is pi over 3. Okay, well, if I want to be really compulsive here, I can do this. 30 degrees compared to 180, and I take that fraction of pi. Okay, 0.52. Well, what is pi over 3? Let's see, I didn't do it wrong. It's pi over 6, right? That's what I said, pi over 6. Okay. if you want, you could say 3 pi over L times 0.30 must equal the arc sine or inverse sine of 1/2. Okay. 3 pi over L times 0.30 has to equal pi over 6. We're solving for L. You see that the pi's go away. Well, I'm going to move this 6 over here. That would be 18. So 18 times 0.3 would give us a length of 5.4 meters. That sounds a little long. Let's see what the solutions manual has to say for number 37. Yes, they get the same answer. I'd like to do this one more way that's a little bit easier. We just reviewed the fact that the sine of 30 degrees, or the sine of pi over 6 radians, is 1/2. Here's one wavelength on the string. The length of the string is longer than one wavelength. It's 3/2 of a wavelength. Well, how many radians does the sine function go through in going from here to there? 2 pi radians, right? That's the period. Not the period in time. In this case, it's period in distance, which is really wavelength. But the argument of the sine function has to go through 2 pi radians to get you from here to here. So what I can do is set up a statement of proportionality. I can say that pi over 6 radians, that's this number of radians here, compared to 2 pi. So pi over 6 compared to 2 pi. Well, that should be the same as this distance in space, which was the 30 centimeters, compared to the whole wavelength. So I'll call this distance in space x, the x coordinate of the place where the height of the curve is 1/2 of its maximum. That should be the same as the distance x compared to the distance lambda, right? 30 centimeters compared to a wavelength is equal to pi over 6 radians. Pi over 6 is where the height of the curve takes on a value of 1/2 compared to 2 pi. If we can find the wavelength, then we can get L from that. So if I solve this for wavelength, I could put lambda over here, see how the pi's cancel. I really have 1/6 divided by 2, that's 1/12. So move the 12 over, 12 times x. Well, x is 30 centimeters. 12 times 3 is 36. So we really have 360 centimeters, which is 3.6 meters. And then lastly, we recognize that the length, because we're in the third harmonic, the length is 3/2 of a wavelength. So 1.5 times 3.6 is 5.4 meters. The first way is probably better because it's more procedural. This is kind of a challenging problem, I think, because you have to think about the amplitude function for a standing wave, and you have to use an inverse sine function. Definitely a problem, not an exercise. And that's all for now. I'll post more of these solutions in the future.